Hello everyone! In this video, I will explain the topic radioactivity and nuclear energy. Firstly, I will outline what you will learn from this video. I will define the nuclear reactions first. Then, I will explain the radioactive decay with the decay equations. After that, I will relate the energy release and mass defect during nuclear reactions and follow with problem solving. Finally, I will illustrate the electrical energy generation by using nuclear energy. Since these are too wordy, let's simplify them. We start with radioactivity, then we go to the nuclear reactions, followed by decay equations. Later on, we will learn about the mass defect and energy release before going to the nuclear reactor. Now the radioactivity. It is defined as the spontaneous or random activity or reaction. The spontaneous activity is not affected or influenced by any factors such as temperature, pressure, or any other physical factors. This is because the activities are present anywhere on the Earth. Now we are going into the first learning outcome. The activity is the activity by the nucleus of an atom. However, the nucleus can also undergo different activities named as the nuclear fission and nuclear fusion as shown here. The nucleus undergoes such activities in order to achieve stability. The elements that undergo the activities are the heavy elements which have high atomic number and are unstable. Therefore, they will decay to become stable. The activities then will emit energy in terms of particle or wave. So, we will learn that radioactivity will produce three types of emissions where each of it will have their own decay equations. And will have mass defect and release energy. Lastly, the energy is useful in the generation of electrical energy. Now we move to the second learning outcome. Radioactive radiation can be defined as spontaneous emission of particles or rays which actually carry energy. The emission is as illustrated here. So, let's see the decay equations. First is the decay equation of alpha particle, which is the nucleus of helium atom consisting of 2 protons and 2 neutrons. Okay, let's see in detail here. X is the parent nucleus, where A is the atomic number and Z is the proton number. After the reaction, the lighter nucleus Y, with a reduction in the value of A and Z here relative to the helium nucleus. Second is the beta particle, which is the electron. Note that the atomic number remains the same, but the proton number increased. What happened here? It is actually one of the neutrons split up into proton and electron. Thus, the electron ejected, but the proton remains in the nucleus, which resulting an increase as shown here, Z plus 1. Okay, lastly, the gamma ray, which does not change the atomic number of the element. It is simply energy released in terms of a wave or ray. Now, let's try to do some exercises on decay equations. We start with the alpha particle and use the decay process of radium here. It decays into radon and emits alpha particle. So, how is the equation looks like? Let's think for a moment. So, the equation looks like this. Did you get it right? Let's move on to the next emission. Beta particle emitted by phosphor. Can you write the decay equation? Take a minute to solve this. So, the equation should look like this. Was it easy to write? Let's move on to the last one, gamma decay. Now, let's try to write the decay equation for iodine. Okay, your equation should be like this. Is it same as yours? If all same, that's very good. But if not, please recheck, okay? Moving on to the third learning outcome. Let's think about this. When we as humans work out, what happened? Can you tell? Of course, we lose some weight or mass, and along the way, energy is released, right? That is the same happen for radioactive decay. So, question ourselves, how can we relate that in physics? We can use the equation by Albert Einstein here. E equals to mc squared. So, E is the energy released during the reaction. M is the mass lost after the reaction. And C here is the speed of light. Now, let's solve problems involving the equation introduced just now. We use the decay of uranium-235 here. Firstly, we calculate the mass defect, or also understood by the mass loss in the reaction. So, we should calculate the mass before and after reaction first, then the mass defect. So before reaction, we only have uranium where the mass is as written here. The mass of the elements can be obtained in any reference books, or you can just Google it. After reaction, we should add the mass of thorium and helium here. Finally, the mass defect is the difference of the mass between before and after reaction. So, we get the number as here. The second step is we change the mass from AMU to kilogram. The constant value here, we can also get from the cover of our calculator as shown here, in case you have not heard about this yet. Okay, so we get the mass defect in kilogram as shown here. Finally, we calculate the energy released by using the equation. And we get the value in joule here. Now we try the second element, uranium-238. Alright, try calculate the mass defect first. I give you 1 minute. Okay, you should get the value here. Next, change it to kilogram and we get the value here. Finally, calculate the energy release. And we get the value here. Okay, for another element, radium. When we calculate the energy step by steps, we get the energy with this amount. So, why do we calculate the energy release for those elements? We want to relate the learning outcomes third and fourth. So, we calculated for these elements and tabulated as here. So, from this table, we want to compare the mass defect with the energy release. Here, we can see that the higher mass defect, the higher the energy release during the reaction. So, we can conclude the energy release is directly proportional to mass defect. And this relationship has speed of light to make it into an equation introduced by Albert Einstein, E equals to mc squared here. Now we have reached the last learning outcome. So, why do we care so much about the energy released by the nucleus? Because actually this energy is very useful for generating electrical energy and for nuclear weapon. Why? Can you imagine the effect of the energy? Can you relate it? Okay, let's see how much water can be boiled by one atom of uranium-235. We use the equation here to calculate the mass where Q is the energy supplied, M is the mass in kilogram, C is the heat capacity of water, which means that how many energy is needed to increase 1 degree Celsius of 1 kilogram water. And lastly, delta T is the change in temperature. So, from our calculations done, we get the energy released by uranium-235 is 7.4724 times 10 to the power of negative 13 joules. And we want to boil water, as example, from 20 to 100 degrees Celsius. And the heat capacity of water is 4,200 joules per kilogram per degree Celsius. So we put in the numbers into the equation and we get the mass of water here. But negative 18 kilograms, it is too small. It is hard to imagine, right? So, let's try to calculate if we use 100 grams of uranium-235. Firstly, we calculate the number of atoms in 100 grams of uranium. Then, we calculate the energy release. If one atom of uranium-235 release 7.4724 times 10 to the power of negative 13 joules, then 2.5613 times 10 to the power of 23 atoms should release 6.5601 times 10 to the power of 46 joules. After that, we calculate the amount of water can be heated up. We get it power of 41 kilogram. Wow, that is too big. What if we think, how many water bottles for this amount of water? It is still big, you see. Power of 40. Okay, let's compare to something imaginable. We use the swimming pool. This swimming pool contains 2.5 power of 6 liters of water. So, we have this amount of water from our calculations, and we calculate how many swimming pools we can get with this amount of water. It is still a big number. Does your head hurt so far? Too much information up to here? It's okay. We have reached to the end. Actually, in nuclear reactor, the activity is nuclear fission of uranium-235. So, your task. Write the equation for nuclear fission. Then calculate the energy released. And lastly, compare the energy released by nuclear fission and radioactive decay by uranium-235. We will discuss this in the next class. With that, I end my video here. Thank you.